Hi folks, thank you very much for taking a few minutes out of your day to watch this video today. If you work with an app that needs to save state in any way, save a file, save settings, that app has to interact with storage. Storage class memory provides the next big step in terms of storage performance and will be important to app developers. My name is Tobias Klima. I'm a program manager in the Windows Storage and File Systems team, and my goal today for the next 10, maybe 15 minutes is to give you an idea of A, what storage class memory is, and B, how your apps can start using it in Windows Server 2016. Let's have a quick look at what it is. And let's use a use case scenario. Think of SQL Server. SQL Server is a database product, and it uses a log structure to make sure that transactions can be rolled back, and you can really get the most out of your database. Now, what this really means is that every time you want to make a database update, you first have to update the log, which makes it a bottleneck. But it also provides you with an opportunity. The faster you can update the log, the more data you can push through your database, the better an SLA you can provide to your customers. So really, if you think about it, let's make the log fast and get the database to get fast with it. And that log could sit on storage class memory. Now, what is storage class memory? We define it as essentially a persistent store, so something that doesn't lose its content when power is lost, on the memory bus directly, very, very close to the CPU. And in Windows Server 2016, we support this in the form of NVDIMM. It's a form of storage class memory. Essentially what it is a RAM DIMM that has DDR4 DRAM on one side and flash on the other, plus some backup power. Could be a supercap, could be a battery, doesn't matter. If power is lost to the system, then what simply happens is the DRAM content is saved to the flash, and on power restore, it comes back into DRAM. And that's what makes this so extremely fast. It can be consumed in two ways in Windows Server 16, either through a byte addressable interface, because it sits on the memory bus, or, and this is much, much simpler, through a block interface that we provide, which wouldn't require any app changes. So your SQL log could just go directly onto the storage class memory device. Before going into the details of how exactly this works, let me step back a little bit and give you an overview of what happened in the storage industry in the last 10, 15 years. If we think back 10 years, everything we had was hard drives. Their latencies were 10, 15, maybe 20 milliseconds. That's how long it took to get your data. And at the time, that was great. All our software was written with that in mind. So we knew I have an unbelievable amount of CPU cycles in the time it takes to do a storage operation. Then SSDs came along. And that latency of 20 milliseconds wasn't the case anymore. Now we could do things in a millisecond, maybe less. And it was great because our apps were snappier, data could be saved faster, could be retrieved faster, and we didn't have to do anything in sequential streams anymore because SSDs had different characteristics. Next, what happened was we put those same SSDs, instead of behind storage controllers, directly onto the PCI bus with their own dedicated controllers and their own interfaces. This further unlocked potential that was basically in NAND flash. And now we're looking at latencies, and this is the fastest storage we can get today, of about 50 to 100 microseconds. Again, significantly faster than what we had previously. And all of this only happened in about 10, 15 years. The next evolution that we see happening here is storage class memory. Now a persistent store goes from the PCI bus directly to the memory bus and can be addressed there. Again, there's two ways of using it in Server 16, but the one I want to focus on here, because it's the easiest to consume for your apps, is block mode. So what does this look like? I have a simple block diagram here, which you can see. You can either use it directly as a disk device or go through the file system. So what we really did was we wrote two new drivers. The first one is a bus driver, which just scours your system and figures out, is there any NVDIMM in the system or not? If there is, the SCM disk driver will load. And this basically hides from you the fact that there are byte ranges underneath and instead presents to the rest of the operating system a disk, just like any disk you have in there today. Could be an SSD, could be a hard drive. The point is, sectors are written rather than bytes. On top of that, an administrator can simply format a file system, NTFS, REFS, whatever you like, And then your app just uses the exact same APIs it uses today, read file, write file, etc., to interact with that storage. The only difference to the app really is that this storage is extremely fast. We're talking about less than 10 microseconds for a random 4K access anywhere on that device. Now, there's one word of caution I want to put out here as well, and that is, at some point, our driver, the SEM disk driver, will have to use memory semantics to talk to this device and make sure your data gets down there. Because of this, filter drivers that sit very low in the storage stack may not work properly. So filters such as accelerometers that sit down there, maybe caching filters, may not work properly because they might be looking for I/O. But if we use memory instructions to get your data down to the device, then there is no I/O. We simply do mem copies or load stores. Now, thinking about the two filters that actually exist most in those areas, accelerometer filters, not much of a problem because they're used to park disk heads when a system goes into freefall. I'm not sure how often servers go into freefall, but even if they did, there's nothing to park on an NVDIMM. There are no moving parts that need to be protected in case of freefall. The second one, caching filters, don't seem to make much sense as well. The reason is that NVDIMM is so fast that all the software we've written in the past that does caching, that does queuing, doesn't make much sense here. It's actually quicker and easier to just do the I/O, don't cache it anywhere, and be done with it. Now, let me actually show you how fast this is. And the hardware we're running on here was provided to us by Hewlett-Packard Enterprises. So let's start the demo. What I'm doing here is very, very simple. I'm just doing 4K random writes against an NVMe SSD from a single core. There's just one thread doing 4K random writes to a 1 GB file on that SSD. And we're just looking at the performance. Now what we see is we get about 55 megabytes per second out of this SSD. Some people will say, but the NVMe SSDs can do so much more. And that is true if you start building up a big queue or you use multiple threads. But everything that comes with that is more latency as well. So what we're looking at here really is how low a latency can we get. Next, what we run is the exact same workload against the NVDIMM. Again, we just expose a disk, we expose sectors, we have a file on this, on a file system, and we're just doing writes. Have a look at how much faster that is. Instead of moving 55 megabytes a second, we're moving about 700 megabytes a second. And you can see the latency difference as well. The fastest flash we get our hands on today, NVMe SSDs, writes at about 68 microseconds. The NVDIMM is more than 10 times faster without any change in the app. And we're looking at 5 microsecond latencies here. That gives you an idea of the benefit your apps could get by running on NVDIMM storage. Now let's get back to the slides we had here. Luckily, I don't need the video I had here because the demo just worked perfectly fine. So a couple closing thoughts before I finish the presentation. Some apps need to do more than just perform their intended function of manipulating data. Some of them, especially enterprise apps, sometimes have to manage device health as well to make sure that storage devices don't die underneath them, or at least they're prepared for it. In order to facilitate that, we integrated management of NVDIMM devices into existing infrastructure we have in Windows and have had for a while. So you can query information about your NVDIMM devices through PowerShell. You can call get physical disk to get information such as name, serial number, firmware revision location, and you can use storage reliability counters to get more information about the device and its health itself. The very nice benefit we get out of this is that we can use the NVDIMM also in other infrastructure we have in Windows. For example, storage spaces, which for those of you who are not familiar with it, is a storage virtualization technology we've had for a while. Essentially, if you have multiple NVDIMMs in your server, you can put them in a stripe set, you can mirror them for resiliency, or say you have a bunch of other storage still lying around, SSDs, hard drives, you can use those NVDIMMs with storage spaces as a write-back cache, such that writes that come in from a given app hit the NVDIMM and the write's completed back to you very quickly. And in the background later, it's destaged to your SSDs or hard drives underneath. So in closing, thank you very much for watching the video, and I'd like to send you home, if you're not home already anyway, with 2 closing thoughts. First of all, if your app could do very fast, reliable, synchronous I/O, which data structures could you use that for? And those data structures, if you have them that rely on very fast I/O, consider using them on storage class memory. Again, this is what we're supporting in Windows Server 2015, and we're excited what you can do with this technology. Thank you for watching.